Good afternoon, everyone, and I'm happy to see you again. So today I'm going to get you introduced to the idea of support vector machines. Now, support vector machines are extremely powerful. They are one of the most powerful machine learning techniques. They can be used for both classification and regression. The concept is under the bonnet is similar for both when you want to do regression or classification in terms of the structure of the algorithm. Yeah, but they vary a bit. Okay, well, obviously it's a very detailed topic, and in this short session, my main objective is for you guys to perfectly understand what this whole thing is all about. Yeah. So we are not going to go into details of it. I expect you guys to then, once you learn what you learned today, is to go and develop on it yourself by, reading more because it's quite big, this idea. Yeah. And what I thought simplifying the the underlying concept, it would help to sort of get you guys comfortable with, like assisting you so that when you go on your own to read about it, you can understand it. Now, I've specifically chosen this picture. As you can see, we have a road, right? And the road seems to be separating forest with green trees and a rocky mountain. We can see that there is a yellow line in the center of the road, and on the edges we see that white line. Okay, so it's like as if this road is separating two trains. Yeah, so let's say that we are classifying greens from rocks, basically. Yeah, it's like as if this road is separating these two classes from each other. Now, whatever falls on the other side of the yellow line can be considered rocks and rocky, and anything falling on the other side of the yellow line, on toward the left, then we can consider it to be trees and grass, let's just assume, yeah? In fact, when we talk about support vector machines and considering your data points, it's like as if we're trying to design this road, yeah, something similar to a road, well, a nicely painted road, yeah, to separate these two classes. Fundamentally, under the bonnet, compared to a linear regression, least square methodology of separating two identities from each other, support vectors work completely different. And the best I thought I can explain it to you is via an example. So if you look at the first machine learning algorithms, okay, we have supervised and unsupervised machine learning models. So we have for supervised, we can be categorized into regression or classification models. Obviously, there is linear polynomial models. We have looked into them before. That's for regression. There is k-nearest neighbor. And then there is support vector regression belonging to the support vector machines. And for classification, you've got logistic regression. Again, KNN is there. And support vector classification, which falls under the umbrella of support vector machines. Yeah. And of course, we got random forests, regression and random forest classification. So today we are trying to address SVMs, and we will touch on some examples with SVC, so classification. But what is super important for me is for you guys to understand the basics, the philosophy of these things. So today, I really want you to pay attention to the philosophy of the idea rather than trying to, find out what the Python code is doing. Yeah, so that's not the objective. Although you will get the Python code, you get to go and practice with it, and I hope you go and do further search yourself. Yeah, but at this lecture, our main objective is for you to understand the concept. So having said that, let's start with a very simple example. Here's something that we are going to be comfortable with. Okay, so let's say we have two genders, men, women. Okay, and these days people choose to dress or look differently. Like uh, ladies or men, basically, they have their own preferences in terms of how they like to express themselves, how they like to dress, how they like to look. Yeah. But usually, I mean, statistically speaking, for example, women tend to sort of dress, or the femininity of women is usually expressed in a certain manner that the macho masculine identity of men, basically, and how they dress and how they try to look, is different. Okay, so if you're walking in the street and you see this guy, for example, on like standing here. Let me just make this a bit larger. So, I mean, let's say we're walking in the street, you see this guy, and technically speaking, you more or less, classifying them as a man, yeah? Now remember, our idea or objective is not here, like we are not looking into sociological aspects of life or anything. It's just an example, yeah? So usually you would associate this guy to a masculine man. He's a guy. The guy with the tie, similar. He looks quite masculine, man-like. Same here. Then you got people who are more fashionable, maybe they like to follow a particular fashion or preference in terms of how they dress, and they are not so similar maybe to this guy or to this guy or to that guy, but they are still men, okay? And like for example, you might say that okay, that's a bit of deviation from the norm on how usually men dress like. Or when you look at women, for example, straight away you see any of these three ladies, the hairstyle, the dress, the makeup. So you usually say, okay, oh, that's a woman. Yeah. Or there might be girls who like to dress more funky. They follow a certain fashion. I don't know. They like to dress differently. And maybe they choose more like boyish style of dressing up. People, they make their decisions. So they would fall into sort of categories like this. Yeah. Now, if we were to use linear regression, let's say some alien came to Earth and wanted to just try to classify male from female, women from men or something. Yeah, they don't have as much knowledge as us. They just capture some images of human beings walking around and they don't know much and they want to see if they can classify this. Yeah. So when they see a group of people, I mean, multiply this by millions. Yeah. So they would try to drive a model. If they follow the linear regression style of classification and separation of data, if they have a linear least square linear method of trying to separate these, what would they do? They would try to categorize, they go by the majority. So they would be like, oh, majority of men probably dress or look something like that, and majority of ladies may go and sort of dress like this, yeah? And they base, if they are following a linear regression, least square linear regression method. So they go with majority from each class, okay, and try to construct a model that is based on this majority, okay? They would try to construct a model based on majority of the observation of what they see, and these other visualizations that they make, they would probably like consider them as like what do you call it, outliners, or the minority basically. So you usually don't see average guy, for example, dressed like this, although you may, but usually you get this in men, or usually you get this in women. Yeah. And that would be the least square method of trying to classify these two genders, basically, for an alien who just is looking at us humans. Now, how is support vector machine model different? Yeah, the support vector machine approach to classifying these observations, if the aliens were going to use SVM, they would go the other way around. Yeah, they would try to come and use in the boundaries of these observations, they would try to pick out the data points in the boundaries, yeah, where these two groups collide, okay? And they would base, yeah, their segregation of classifying these two sexes by using the edge data. Hence why, if we go back to this, the original image, as you can see, it's the edges of the mountain, yeah, that there we are caring about. We are not going deep into the mountain in the rocks, basically, but it's the edge of the rocks and edge of the grassland, yeah, that we're trying to construct this road around to separate the two classes. And that's exactly what support vector machine approach into classifying these two sexes based on the visualization is constructed upon. I hope this makes sense, because you need to realize that support vector regression model works completely different to the linear least square linear regression approach. Yeah, okay, I hope that helps you first understand where we're going with this. Yeah, I mean, this was the best example I could come by. Okay, now to reach the idea of support vector machines, yeah, we need to go through evolution. Okay, we need to go through, so before we discuss support vector machines, we need to first address two things: maximum margin classifier, okay, maximum margin classifier concept, which leads to support vector classifier, and ultimately evolves into a support vector machine. So we start with understanding maximum margin classifier, then we evolve and we develop it into support vector classifier, and we shoot into support vector machines. In fact, what we did here, we did a hard margin, maximum margin classifier, okay? Right away, we came and said, clear cut, that's it, yeah? We are going to choose these women as the boundary of classifying women, and these guys as the boundary of classifying, for men. All right. This was really the maximum margin classifier approach. Yeah. Why do we say that? Because this doesn't leave any room for misclassification. Okay. This approach, maximum margin classifier, would not allow any misclassification. It needs to be pinpoint perfect. But when it comes to classifying data, we all know that classes don't separate like this. Yeah. So you can have data points which may not be as clearly separated from each other. They might be entangled. Yeah. Firstly, let me also introduce you to the idea of hyperplane. Yeah. So in geometry, a hyperplane is a subspace whose dimensions in one less than that of the ambient space. I really like, I don't want to spend too much time on this, but I really like you guys to go and then read about this. In other words, in the example of the road that we made, that yellow line is our hyperplane, technically speaking. Okay. The yellow line is that hyperplane that is separating the two subspaces. Okay, and definitely expand on this on your own. Yeah. For example, here, if we were looking at we are looking here at like a 3-dimension of data. Here X, Y, Z. Now that hyperplane is going to be 2-dimension, isn't it? It's like a surface basically separating these two. But when we go to 4, 5, 6, 7 dimensions, obviously we can't visualize it. but you need to know that always the hyperplane is going to be one dimension less than your underlying data. Just know that, but definitely expand on this yourself. Now, when we talk about that yellow line and we are talking about the rocks and the grass, well, we are going to, like data is like data points, isn't it? The rocks, you can imagine it as data points. So when you want to draw that yellow line, obviously you need to measure the distance of your data points on the rocky side to the yellow line somehow. And this is the formula for measuring the distance of a point to a line. Again, I expect you guys knowing these. We can't spend time on this. If this doesn't make sense, you need to find out about it yourself. Just Google it. It's A-level mathematics, basically. Yeah. So this formula demonstrates the idea of how to measure the distance between a point and a line using the formula of a line. So that's a formula of a line, this blue line, and the point will have some coordinates, okay? And this is how we go by measuring the distance of this point to that line, okay? So expand on this yourself if this is not familiar to you. It's not difficult, but you need to understand it, okay? All right. Here, support vector machine is one of the most popular algorithms in machine learning. We have already mentioned that. It's a powerful supervised algorithm used for classification and regression. What you see on the left is the idea of classification, which we already discussed. And what you see to the right is when you try to apply this model for regression. I want you to, at the moment, forget about the regression idea. So we are not going to talk about the regression. We don't care about it. I want you to understand the concept. So these are all classes, let's say men, women, okay? And or like the mountain, the rocks, and the Greenland, basically. And that's the road that we are talking about. And look at our support vectors that we try to define and design this road with. Yeah. We use the edge data. We don't come and use, data points on the far end. Yeah. We don't use the majority, try to find the least square distance, of these points and the line, just like, the approach with least square regression. Rather, our approach is to pick out the edge data and maximize the distance between these two edge data, and then try to design that road. And this is that yellow line, basically. So that's what the idea of support vector machines for classification is all about. Yeah, getting your data and then trying to draw this road such that you maximize this distance. Okay, so that's what SVC, support vector classification, is all about. Now, we talked about a hard margin. Yeah, for example, in this example, we got the purple ones and we got the blue lines. Yeah, well, it's obvious that you can separate these two, no problem at all, because the purple ones are perfectly independent of the blue ones. They're separate. So you can come up with choosing your support vectors. Support vectors are the points on the edges, and then maximizing the margin between them to draw that road, that beautiful road, where the white line indicates the, support vectors, and the margin is the yellow line separating the two, yeah, for your classification. That's the MMC. As I said, we need to evolve from the idea of MMC to then understand support vector classification. So if the world was perfect and all classes or any data that you had for classification were separated as such, happy doopy. We just have an MMC approach, everything that we have discussed so far. Yeah. And ignore these mathematics for the moment. Yeah. So the core idea of hard margin is to maximize the margin under the constraints that the classifier does not make any mistakes. As I said, there is no room for any mistake. Yeah? And we want to separate these two. All right. Well, what if we start having data? Yeah. What if we start having data that, applying that condition is not possible? I mean, for example, something like this, yeah? Something like that, or something like that. Like here, look at the orange dots, yeah? This orange dot here is very, very close to the blue ones, yeah? So when you look at this, obviously the dashed line seems like a better separation line between them, isn't it? But this is your training data, and you know that the orange line, which is falling very close to the blue lines, is part of the orange group, okay? So you have to go by, if you want to, separate them, if you want to draw that yellow line, yellow marking on the road, you need to go with this solid line. And then you're like, oh, okay, but that doesn't make me feel comfortable. That orange one really shouldn't be part of the oranges. It should really be part of the blues, okay? But MMC doesn't allow for that. And then if you come to something like this, this example here, the third one, the data is non-separable, overlap. Well, MMC is going to fail. It won't happen. Yeah, there is no way ever that somebody would be able to come and say, well, guess what? I'm going to use a straight line and separate these two classes, the blues and the oranges, from each other. You cannot, with a hard margin, yeah, separate these two. And that's where the idea of SVC, soft margin, comes in. Okay, so the solution, we can extend the concept of separating hyperplane, remember the yellow line, in order to develop a hyperplane that almost separates the classes using the so-called soft margin. What does this mean? It means we are going to allow it to have some errors on the training data. So we're going to say, do you know what? We don't care. Let's just make some errors while we run our algorithms. Yeah, we're going to make some mistakes. We're going to consider some of these orange lines just to be blue. We don't care. We're going to accept that some misclassification is going to happen. So it could be worthwhile to misclassify a few training observations in order to do a better job in classifying the remaining observations. Okay? Otherwise, you cannot. Simple as that. And that's where the idea of soft margin pops in. So you back down a bit. You negotiate with your data. Okay? You're negotiating. You're like, okay, I need to make some misclassification so I can develop a model. That's soft margin, SVC concept, evolving out of the hard margin concept. Yeah. Let's look at this. But then, to evolve this into a proper support vector machines, you come and say that, all right, I'm going to add some more mathematics to it. I'm going to add some penalties. So I'm going to allow it to make some mistakes. I will allow it to make some mistakes, but I will punish it for the mistakes it makes. Imagine your kid, yeah? You want to tell your kid that the rule is you're not going to have anything with sugar in it. Why? Because everybody says sugars and chocolates are bad for kids. If they are, I don't know, yeah? Again, I don't know if you believe is that you should give chocolate to children. I don't care. It's just we are using this as an example. So, but if that's your rule, that I don't want my kid to have any chocolates, a strict rule. Well, your kid is going to go to a school. He's going to go to camping. He's going to go with his friends. And probably they're going to give him a chocolate or something. So you can bend your rules and you can agree that, all right, sometimes he can have a chocolate. But then you put a penalty to it. Well, if you eat two chocolates when you were with your friends, fine, but then you can't watch telly, or I don't know, you're not going to have your iPad or something. Yeah, so you add a penalty to it. So let's look at this. So as we are evolving from soft margin into the concept of support vector machine idea, soft margin classification adds a penalty. Let's call it C, well, it is C, to the objective function for observations in the training set that are misclassified. Yeah. In a sense, the SVM algorithm will choose a decision boundary that optimizes the trade-off between a wider margin, maximizing this margin, and a lower total error penalty. Okay? There is this thing called the slack variable that allows some observations to fall on the wrong side of the margin, but will penalize them by a parameter called C, cost of misclassification. All right? Again, let's not fall into the mathematics of it, but once you understood it, I'd like you to go and learn about it. But at the moment, just understand that, okay, we can't always have our way. We can't always separate these two perfectly. There is going to be some misclassifications that we need to allow it, but we're going to punish our model for those by something called C through these slack variables of how much basically error they're introducing to our model, all right? So that's where you start to basically evolve your soft margin model into maturing into a support vector algorithm, okay? I've put some notes here basically. So large C, large penalization, gives a small margin, so it gives low bias and high variance. And a small c leads into large margin, which is high bias and small variance. We have covered bias variance before. I can't spend time on it before, so make sure you understand it. But then something like this comes up. You know, sometimes you can have a data like that. This is where we fully mature the idea of a soft margin classifier into a support vector machine. Yeah, this is where it materializes, you know. So look at this data. Is there any way at all that you can separate these two with a straight line? Even if you say that, oh, I'm going to be really lenient, I'm going to allow for some errors. Yeah, you can allow it, but there is just no way. You absolutely have no way of separating these two with a straight line. It won't happen. Okay? But then how are you going to come up with a hyperplane to separate these two? Okay? So we want to separate the blue from the yellow. Okay? And it has to be a straight hyperplane, sort of. Yeah? It can't be a curvy one, technically. So how are you going to separate these two from each other when you have a problem like this? And that's where the beauty of support vector machine idea comes in, where you go into higher dimensions by using a function. Okay? So your original data in this simple example is two-dimensional. You have X and a Y. Okay? You have X and a Y. So to be able to apply support vector machine algorithm into classifying these, you need to come up with an idea to increase the dimension of your data. So non-linearly separable data, sometimes a linear boundary simply won't work, as we just discussed. No matter what value of C, no matter how much you want to punish your model, it just won't happen. So, and we need a non-linear decision boundary. So how are we going to do this? So we map it into a higher dimension, okay? How does that work? It's by applying a particular function to our data. The simplest is to square our data. Okay, that's one way. Or there is the kernel trick. For example, radial basis function. Okay, which comes and applies on your data and takes it to a higher dimension. Obviously, this is a two-dimensional, but we are increasing it to 3 dimensions. Now, when you increase it to 3 dimensions with a kernel trick, yeah, then you can use a hyperplane to separate them like that, yeah. And that's where the idea of, you know, support vector machine model all falls into. Again, don't worry so much about the mathematics of it at this stage. Just try to visually, conceptually understand what we're talking about. So the fact is we can use these functions, okay, under the bonnet to take our data in an artificial manner to a higher dimension to be able to separate them from each other, okay? And then that, you know, this line basically that comes out of this hyperplane can be the circle that then separates these two, okay? let me not go into that. I think that's enough for this at the moment. So let's go and do some Python work. Okay, let me reconnect it. Okay, how much time do we have? Okay, so I will quickly go through this and then I will run an example for you after that. Yeah. So let's run this, guys. We are going to just generate some random points. Yeah. So I'm going to run this. Super simple, right? This is our classes, like men, women, I don't know, grass, rock. Yeah. So we have this data and we want to apply support vector machine concept, like into separating, classifying these two. So we want to draw a line basically separating them. But what do we need to do? We need to use the edge data that are closest between the two classes and then draw our line by maximizing the distance of these edge data points to that central line. Yeah, that's what we want to do. Let me pass this. So if I just come and say that, okay, okay, is that a good point? I mean, like I chose this linear sort of line, this line. Yeah, so let me just change this. All I did, guys, I just changed the formula of the line, yeah? So nothing super. When you are doing this, you can copy the code, you can pause the video and copy the code and see what's happening. This is just basic stuff, with matplotlib, plotting points and all that we have done before, okay? So, all right, is this line working? No, it's not. Hence why going with the other line looked better, didn't it? So if I just do that, so this line looks good, more or less, but obviously mathematically it's not proven. It just looks good because I played about with these numbers and tried to get it there. Is that at the moment support vector machines? No, it's not. This is just a line we drew. But it needs to be mathematically validated based on the theory and the concept that we discussed earlier. Okay? So if I come on now, let me hide this one because I made two of these. Let's look at that. That wasn't the idea. Sorry. If I put in. Okay. Well, technically speaking, this is something like what we want to do mathematically. So we need to draw these lines. Okay. Now, obviously, let me give you a heads up. We are not going to do support vector machines ourselves. We are not going to write the entire algorithm ourselves. We're going to do it via scikit-learn. Yeah. And I'm just showing this to you so you understand. Otherwise, nobody goes and writes the code for support vector regression or classification. You don't even need to learn it. Yeah. But the idea is this: you come up with a random line, okay, and then you try to measure this distance. Okay. Let's think about it. That's how you would do it mathematically, and you would loop it through, trying to find the um, 2 points that maximize the distance between the adjacent sort of points between these two classes. All right. Then we go here, and let's say we come up with these 2 points. Okay. So mathematically, we find out once we do all of that, we find out that look, the 2 points that are closest are these, and we are going to consider using these 2 points as our support vectors. So we can draw that yellow line, the road image basically between the rocks and the grass. So we can construct that yellow line in between. So mathematically, we go through searching these distances, finding these 2 points, and then trying to now draw that line so that this distance between the two is maximized. And if I run this code now, so again, I'll leave this here in case you want to, like copy it, so you can pause the video and copy it. So I'll just leave it here and then I'll move on. And there we go. So you draw that line, okay? Technically what we are doing, pay attention guys, we are doing the hard margin approach, yeah? We are not doing support vector regression, so support vector classification. We are not doing support vector machines yet. We are just going through that hard margin approach. Well, that's technically what you would do, yeah? If I draw this line now, so again, let me put this code on so you can copy it if you like later. I don't recommend doing it even, but in case you're interested. Okay. What did I do? What happened? Look at that. I didn't do it really myself, did I? In fact, I don't know how to write the code for SVC. It's really involved and complicated. So I'm importing the model from scikit-learn. So from scikit-learn.svm, import SVC, support vector classifier. And then I make an instance of the model, and I'm using c equals 1. Remember that? Let me just go now to this. So when I'm defining my model, do you remember c? So we have now moved into a support vector machines. So I'm adding a kernel, and I'm adding a c, a penalty of 1. Okay, so low penalty, I'm being lenient. And I'm asking SVC to go and draw the line. This was a line that we tried to draw with hard margin approach. This is now using SVC, yeah, the algorithm embedded in with scikit-learn, proper support vector machine algorithm. And we're going to ask it to draw the line. And let's take a look. And SVC goes and presses. So that's the dashed line that I came up with, which seems was rubbish. And now support vector machine model would come and draw this black line, okay, which is perfectly calculated by undertaking the calculation of every single data point and trying to maximize the margin between these two classes. And that's all that it does basically. So remember, this was not done by me, it was done by SVC from scikit-learn, okay? So that's the concept. Now, what if I was to, in the case of this data, what if I was to use c equals 100, penalize it? Are we going to see any difference? Let's see. Not really. It's the same thing. It's exactly the same thing. So why is that? We thought like if we add penalty to it, something would happen. Well, remember, for a data like this, which was easily separable, the hard margin MMC, yeah, maximum margin classifier, worked. Remember, we said that SVC applies when basically there is no solution out. You rely on support vector machines. That's when they become powerful. When these two data sets are not as easily separable. Hence why I generated some other random numbers. So just to illustrate this to you. Where was it? So that's the first one, first set of data. Remember, this is the first one we worked with. Now I'm going to run this one, exactly similar to this code, except that I'm getting these data closer to each other. Look at that. Now it's going to be challenging, isn't it? Trying to separate these two. Because hard margin approach, it just won't work. There is no way you can perfectly separate the yellow, sorry, not yellow, the red from the blue with a straight line. Okay, so if I go and do this now, not so much bothered about this. You see, like things start to get complicated. And if I do that, okay, that's me trying to find the two nearest point with just a basic algorithm, it's not working, is it? So how are we going to sort this out? Let's see. No, complete rubbish. So let's go with support vector machine model. Okay, and that's what it does. Yeah. So imagine that dashed line is what I tried to do. Now support vector machine model now tries and decides to go with this line to separate the two classes from each other. Okay, and that was with c equals 1. Now if we go and go c100, meaning we're going to be punishing it basically significantly, you will see that it will start to alter. It will make some changes. So as you can see, like it becomes slightly different, but this is a simple data. Now, having said that, we are 1850. So let's go and now look at example. Yeah. So I've written a code elsewhere, and I'm going to just copy and quickly run this. So I'm going to say file. What do I want to do? File, new notebook in Drive. Okay. And of course, you guys, I just want you to watch it. You don't need to code with me. Later on, when you watch the video, you can. So we are going to import some libraries. Okay, so we are going to work with some real data now. So you can see how you run, how you use support vector classifier. So I'm importing pandas, I'm importing NumPy, importing matplotlib. I don't even know if I need Seaborn, but I don't know why did I put it. Okay, so I'm importing the libraries. Now from scikit-learn, there is an embedded data, breast cancer data that you can load just for practice. So from scikit-learn.dataset import load breast cancer. Okay, and then you're going to come and say cancer equals load breast cancer as a function. This creates the data for you. So this is a scikit-learn embedded bunch of data. Okay, if you now come and look at cancer, it may not make sense to you. So it's just a lot of data in there. Okay, these embedded data, you need to sort of extract it in a particular fashion. So we're going to say just, so we're not so much bothered about the data, guys. Yeah, I just want us to sort of see it. So cancer.keys, the keys are data, target, frame, target name, description, feature names, file name. These are all embedded. You have downloaded all that information as cancer. Okay. Um, let's get to the point and find out the features. Actually, what do we do here? Okay. There's a feature names, isn't it? Yeah, cancer feature names. Yeah. So because we have that cancer feature names, we're going to say cancer feature names. It's like a dictionary, isn't it? Okay. So if I say cancer feature names, these are the feature names. So this data has been looking into cells, yeah, biological cells. It has data about the mean radius, mean texture, mean perimeter, mean area, blah, 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 blah. Certain parameters about human cells, okay? And ultimately a classification on whether they are cancerous or they are not cancerous. So we're going to make a data frame out of this. And we're going to say dfx or x data equals pandas.data frame. Cancer data, remember, we are all getting all this stuff from here. Yeah. You don't need to memorize any of this. This is just the data. You follow this as it is for the sake of just getting the data when you are redoing this. Yeah. So pandas.data frame or data, cancer data, column names, cancer feature names. That's all. So that gives us our DFX. So if I say DFX.head, that's what it is. Yeah. So we have a data set of, certain cell features, mean radius, all the way to worst symmetry. And I don't know, I mean, like you need to be a cancer biologist or something to understand this. But we just know these are the data associated with cancer cells. Yeah. Or are these cancer cells or which is cancer cell, which is healthy? Where do we get that data from? Let's see. Here from targets. Yeah, this would be like 0, 1 telling you if it's a cancer cell or if it's a healthy cell. So if I say cancer bracket target, okay. So 0, 1, 1, 0, 0. But if it's 0, it's not cancer cell. If it's 1, it's a cancer cell. Okay. So we need to start making our test and training data from this. But before that, let's make a data frame of this thing as well. In fact, I have written it already. So let's copy paste that to save time. And then let's look at dfy dot head. That's it. So we just converted this into a data frame, except that it's just one column, isn't it? So what are we going to do, guys? We're going to use this dfx as our x data, and we're going to use this dfy as our y data, uh, which we're going to predict. Yeah. So let's get train test split, which we have covered before for splitting our data into our, like splitting the data for a model. Because obviously for machine learning model, just a reminder, we need to have training data to train our model, in this case, a support vector classifier. And then we need test data to then find out how good the model has learned, basically. So from scikit-learn.model selection, we import the train test split, okay? And then we're going to do x train x test, y train y test equals train test split. So we use dfx for our x data. Yeah, this is our x data, and we're going to use dfy, which we just created from these targets, and we're going to use 30%. Yeah, so use or not use, keep 30% for testing. So technically, we are using 70% for training the model. Yeah, good. Now, obviously, as I said, let's use scikit-learn to get SVM. Okay, let's use it. Okay, control N. Now, from scikit-learn.svm, import SVC, support vector classifier, in capital letters. When you want to do regression, you do the SVR, but we are not doing regression, we are doing classification. So if I do that, I have now imported the SVC from SVM. So this is support vector classifier, okay? And we are going to make it vanilla, basic, super basic, yeah? We are not going to change any parameters or anything. We are just going to go with the basic model, simplest that is available. So we're going to say model. We are making an instance of the model, yeah? SVC, that's it. I'm not introducing any, you remember C, the penalizing parameter, or the activation, sorry, or the function, basically, that the kernel function. I'm not defining any of that. I'm just using the vanilla, straightforward SVC model. That's it. That's our model. And what am I going to do? Just fit the model with my training data. So I'm going to say model dot fit. What am I going to fit it with? X train and Y train. Okay, that's it. It depends on your also computer. Well, of course, this is a small data, yeah. But usually this can take long depending on the computer that you're using, of course, yeah. So if you use your own data or like for your own projects and it's a ginormous data, expect that this would take some time. But for such a small training data, HappyDuPy straight away it does it, yeah. Okay, so perfect. We have done this now. What are we going to do? One thing that is important is okay, let's do it this way. Yeah, actually, let me put it because some of you may make a mistake later on when you come to do this. Just DFX, guys. The shape of our DFX is 569, 30 columns. Okay, so we've done this stuff before. DFY shape, it's 569 rows and one column. Okay. If I go and do, yeah, let's do it like this so you can see what would happen. Yeah. Okay. If I go back to this, where I made the instance of the model and we run it, although this was run, let's look at this, yeah? Data conversion warning. A column vector y was passed when a 1D array was expected. Please change the shape of y to n comma samples, for example, using Ravel. Okay? What does that mean? Yeah. It means that the SVC model doesn't like this shape, yeah? So let me write it. SVC does not like the shape of the target. Okay? It wants number and then comma, like this, yeah? And that's how you do it. Why? Because if I do okay. dfy.iloc all the rows first column dot shape, yeah, it will convert it into a single row, a single number line, basically, yeah. That SVC wants it. Hence why I thought like I showed this to you so that you know why I'm putting yloc here, so you don't get that thing anymore. So adjust all we did here with this iloc, I changed the shape so that it can, you know, make it stop whinging. So what I'm going to do now, we are going to do exactly what we did before. So it's like, remember here as a note, we rerun the train test. So we were not happy with this because this is not good, yeah? So we're going with this so that that shape is satisfied, you know, because SVC is fussy about it, yeah? So if I go and say now model.fit, so again, we're going to fit it. Hopefully we shouldn't, why did it do that? Ah, because I didn't run this, okay? That's why I'm looking. Okay, so we are not getting any warning or any whinging from SVC, yeah? We just did it. So our model is trained. So let's make some predictions. Predictions. Prediction. Let me actually use the one I've written so that in a short time. So predictions equals model, which is trained now, dot predict x test or x test data basically. There we go. We have our predictions. Okay. And how do we, I mean, we have done this before. How do we go by finding out if our model has done a good classification? Always confusion matrix classification report. Yeah. So from scikit-learn.metrics, we import classification report and a confusion matrix. That's imported. And then let's go and say print confusion matrix and of or y test versus our predictions, okay, to see how well did it do. Let's do that now. Ooh. So 50, 105, and it made 16 mistakes. Okay, it still has done good, but don't forget, guys, this is for cancer. We can't have any room for error. If you come up and you say, oh, great, look at me, I came up with a model to predict cancer cells. I did 155 correct, only 16 were wrong. Well, they would throw you out of the room. For identifying cancer cells, you really need to be 0 and 0 on here. Instead of 3 and 13, there should be zeros. So how can we go and basically, you know, let's just do the classification report as well. At the moment, I don't care about the classification report, but just for the sake of it. So that may seem good, but it's rubbish for this concept. If this was credit card default, the guy not paying his credit card bill, or the possibility of the guy not, you know, spending the way you like to spend on the holiday with your credit card, yeah, okay, it's a good model. But for something like cancer identification, that's total garbage, yeah? So we would be like, all right, let's go and improve on this model. How are we going to do it? We're going to use grid search. Okay. This is where the beauty of, so let's get pro with SVC, SVM actually, by, using the relevant parameters. C, there is this thing called gamma and a kernel. Okay. Control. Okay. So we're going to make a dictionary first, guys, and I hope learn this idea of grid search basically. Yeah. So first, let's define these parameters. Look at that. Why am I doing this? Well, when I did SVC here, when I define SVC, that model, what did I do? Model equal. So one way was to do model equals SVC, okay? And then you will be like, C equals this, I don't know, gamma is that, and kernel is that, and keep running and running and running models to find out which of these parameters, which C, which gamma, and which kernel would be working best for you, yeah? So you would be sitting there running this, changing this all at, one after another. But you don't do that. What you do is that you use grid search, yeah? So this is rubbish, yeah? So don't bother trying to change these one by one. Instead, use sklearn and its grid search tool. Okay. How do you do it? We're going to make first. Sorry, we need to import grid search CV from scikit-learn, and you can import. You can use grid search CV for a variety of models, not just for SVM. Yeah. Read about it. You can use it with other algorithms as well. So first we import grid search CV, then after we have, so as I said, this is not exclusive to SVM, has application in many other models. In fact, in future we may use it for other sort of stuff. Yeah? So I imported grid search CV. Now I'm going to make an instance. Now I'm going to make an instance of grid search CV. And in that, I define my model, which is going to be SVC, parameters, which is this, the parameters that I want to be adjusted, yeah? And refit equals true, okay? Which means just keep doing it, basically, yeah? Going and basically trying to find the optimum sort of, solution, the best margin line, that yellow line. So what we are saying, what we are doing here is grid. Go and pick up a SVC model and try using all these parameters in combination and come back to me with the best parameters for C, gamma, and kernel. Well, kernel, I've just put one kernel, yeah? We're just checking C versus gamma. And tell us which SVC parameters are going to work best for us, yeah? So I'll make an instance of grid. What did I do wrong here? It's because I didn't run the parameters, sorry. Okay, so grid is made, an instance of grid is made, but it's not fitted on our data yet. So grid at the moment is equipped with a support vector classifier model. It is having a dictionary of parameters to use, a multiple combination of parameters to use on that SVC. And it's ready to go, but there is no data to it yet. Yeah, so we're going to say grid dot fit extract train. Exactly the same data that we gave to our SVC, yeah? Y train. And again, especially if you have a large data, guys, be aware, if you have a very large data and you do this, and depending on your computer, this can take some time. So now I'm going to run it. I have a quite powerful computer, so it does it quickly, usually, yeah? And the data is not big. This data was not big. But just imagine if you wanted to do this one by hand, how much of your time would have been wasted? So we just did it. Now, just remember, let me put this here. Just remember your model is not called model. Yeah, it's the grid. Just be aware of that. Yeah, don't come and say model.predict. Yeah, it's the grid. So first, let's get the best parameters from there. So we say grid, which was fitted on our data, dot best parameters. So it has calculated that the best parameters are to use C10, so penalizing it by a factor of 10. Gamma is 001. I will explain to you what this gamma is in an analogy in a bit, yeah. And kernel, of course, we just went with RBF, yeah. So at the moment we're going. Usually when you have multi-dimensional data, you go with RBF anyway, yeah. Definitely you don't want to go with linear, okay. Let's make predictions. So shall we call it let's just keep it separated from that. So I'm going to say grid predictions. I could have called it predictions or preds, but just so that you know that we're using the grid to do it, we're going to use grid prediction. We're going to say grid. So remember, not model.predict, grid.predict. Or model is the instance of SVC that basically was a very basic sort of thing. X test. Is everything right? I haven't made a mistake. All right. Grid predictions are made. Cool. So are we going to have anything better on this? Let's just take a look. So with our confusion matrix. So again, we are doing exactly the same thing. You know, this let's see if we have made any improvement, hopefully. I hope it doesn't embarrass me. Oh my God, it didn't get that well, did it? Well, it comes with 5404.49. Did not really make much improvement. Yeah. So when this happens, okay, in fact, I had run this before as well. You could get certain improvements. I went as good as getting, I think, before earlier on when I tried it, I had as much as 57 here, 110 or 11 here, and 2 or 2 here, something like that. That was the best I could. Yeah. So what does that mean? Can this be a reliable model for cancer cell sort of detection? Well, not really. Yeah, maybe it's not acceptable. So just because a model is sophisticated, it doesn't mean that it would always answer to you. You can make improvements, okay? You can make improvements. You can try to sort of even go and use a different kernel functions. And in fact, I want you to do that. Yeah. In fact, I want you to do that. Try to use different kernel, like use poly, yeah, or I don't know, like use linear if you like, yeah, and see what you get. All right. Now let me just open something so I can, because I wrote it somewhere. Okay. Just as a closing note, yeah. So ultimately, we went by, we used the grid search, tried to choose the best parameters that we could with, you know, grid search CV and pick out the best parameters for SVC. Or in other words, you can make your SVC manually by now inputting these parameters into it. Or if you don't trust it and you believe it didn't do good, you can even go by changing them, something close, yeah, and see if you get any better results, yeah. But ultimately, you need to know why these parameters, what do they mean, yeah. So if I use an example of, like to close the lecture, imagine I'm your lecturer and I want to evaluate the guys in the class, yeah? Imagine the guys in the class and I want to evaluate your marks. And then I want to set up exam questions based on your performances, yeah? So the gamma in SVM, the gamma value that we use, is like me as a teacher when grading homeworks, in a classroom. Like if I use a high gamma, it's like as if I'm a really strict teacher and I'm focusing on some of the students sitting right front of me. Yeah. If a few of these students give me unusual answer, uh, you know, I as a teacher will adjust the grading rules just for them. Yeah, the people that I see in my sort of vicinity, those students who are nearer to me. Okay, and I would make the grading highly specific based on my observations, based on those students that were sitting in front of my bench, in front of my desk, like in the class. Yeah. In other words, in SVC, the gamma, okay, a high gamma means how many of the points in your data set you try to adjust the model basically with. Yeah. And I'd like you to really go and read about these, right? If I use a lower gamma, yeah, it means that I try to consider every single student in my class. I would be asking everyone a question and trying to come up with exam questions that fits to everybody's sort of response. But that's not good, is it? Because I might have one really, really lazy student. I'm sure you guys are not like that, but like imagine there is one of the students, I tell them what is 2 plus 2, and he says, oh, it's 5. And I'm like, it's okay, you're improving. Last week you said 6, this week you said 5. And I'll lower the quality of the exam questions to ensure that even he passes. Yeah. So a very low a very low gamma means that I'm letting all my data points to have a say on how I'm defining that yellow line. Remember that yellow line from the row? And a high gamma is like I'm just trying to make the exam questions to those 5 or 6 students who sit near me, the ones near the edge where we define the data. And because these are the students who are constantly reading papers and they are really sort of into it, and they are even better than me, so I end up giving massive questions that the whole class basically fails, yeah, because I try to make it over a street. So as such, it's important that you sort of, when you define a SVM model, you go by choosing the right sort of number. Now, I really, really like you guys in your own time to go and play about and try to see if you can adjust these, yeah, and see if you can get better results than this. Obviously, if you're doing it randomly, you would get a variation. But try, I mean, like as a fun, see if you can get these two corners zero. I haven't been able to, but then because this is a scikit-learn training data, it's not anything real. Or find out and read. Go to ChatGPT, say that, yeah, I'll use this data, and just with the support vector machine and grid search CV, I'm not getting anything better than this. How can I improve it? And that sort of lays the foundation for you to thoroughly start understanding support vector machine. And as usual, I didn't manage to finish on 7:15. Okay. Uh, oh, and I will also put a video on an exercise for you this week. Yeah. So later on tonight, you will get an exercise problem. I'd like you to try it, but this is simpler than this. But then I have a video recorded from before that shows you how to solve that exercise. Try to solve that exercise first. If you couldn't watch the video, or like watch the video and try to solve the exercise as well along with it. All right, guys. Well, have a great evening, and I can go and have my dinner now. Okay? And I'll see you next week, hopefully. I hope you enjoyed it, and bye bye. Thank you very much, Francis. Yeah, I had to go through recovery basically. So I had this operation on my sinuses. The good thing is that I don't snore as much at night, which is great. Yeah. No, not much more, complex. Okay.